Hey guys, today we're going to take a look at some applications of sinusoidal functions that we've been learning in this unit so far. So earlier in this unit we graphed the sine and the cosine function, and I just want to dive a little bit deeper into kind of what the sine function is tracking and what the cosine function tracks in relation to the unit circle from our previous unit. So I'm going to take you over to a little applet here, and we're going to first take a look at the sine function. So the sine function, because we know from our previous unit that sine is actually y over r, when we look at the radian circle or the unit circle, the radius of the unit circle is actually equal to 1. So we get y over 1. And simply what we want to do as we track this little red point as it moves around this circle is look at how far above or below the x-axis that point is. In other words, I'm tracking the y-coordinate of this point. So let's take a look at our usual 0-degree point. Where is our point here? And I'm talking about the vertical displacement of this point. So is it above the center, below the center, or equal with the center? So if you said equal with the center, that's because the y-coordinate here is equal to 0. So at 0 degrees, we have a point 0. And then you're going to kind of see here that as we look at the right triangle that gets formed as we rotate our point around here, that we're actually looking at the y distance of that point. So we're looking at its displacement above or below the center. So you're going to kind of see how that relates to this y coordinate over here. So if we rotate up 90 degrees from where we started, you're going to see that we are exactly 1 unit above the center. And that's why at 90 degrees down on our graph here, we're 1 unit on the y-axis. Okay, and then as we start to rotate around further here, you're going to see that your height of y gets smaller, and that's why our point moves closer and closer to the x-axis here. So at a full 180, we are now equal with the center again, which means that we're now at 0, a vertical displacement of 0. We're not below or above the center at all. Okay, and then as we continue to move around here, you're going to see that as this height increases, we're getting more and more negative here, and that's because we're in the negative section of the y-axis. So if we move all the way around to our 270 point, you're going to see that we're now 1 unit below the center, and that's why at 270 for sine we have a point at -1. And then finally, if we rotate around to complete our rotation, we have now rotated 360, and we're back at a vertical displacement of 0. So that's why we have a point at 360, 0. And then basically anything that we do further from this, our point is just retracing its steps. So if I do another rotation, now I've gone from 360 to 720. And that's why this function really is periodic, right? Because every rotation that I do, the point returns back to its same vertical displacement again and again and again. All right, now let's take a look at cosine. So if you remember back from our previous unit, cosine actually tracks x over r. And in this case, for the unit circle, our r is actually equal to 1, has a radius of 1. And so I'm looking at how far to the left or to the right of the center our point is. So at 0 degrees, our normal 0-degree location, we're actually 1 unit to the right of the center. And that's why cosine actually starts at a maximum. It starts at 0, 1, because we're actually completely the furthest over to the right that we could be to the center. And now if we rotate 90 degrees, you'll kind of see how this x distance here starts to shrink as we get closer and closer to this 90-degree point. And at 90 degrees, are we to the left or the right of the center, or are we equal with it? Okay, we're equal with it now. So now at 90 degrees, we're actually at 0, horizontal displacement of 0. Then we're going to continue rotating. You'll see that this x distance is now getting larger and larger toward the left or in the negative direction of x. So if we rotate a full 180, you should see that we're actually 1 unit over to the left, which means that we're actually at a horizontal displacement of -1. Okay, and then rotating back toward 270, We're now equal with the center, so that means that we're at a horizontal displacement of 0. And rotating over, you can see that your x displacement is now growing again. And at 360, we're back at a horizontal displacement of 1. And then, like I said, with the previous one, any rotation that we do beyond that, we're just retracing the steps of that first rotation. And that's why this function is periodic. Okay, so basically our findings are this. Our sine function essentially tracks the vertical displacement of a point as it rotates around the unit circle. And that's also because we know from our previous unit that sine of theta actually tracks y over r. So it makes sense that we should be tracking the vertical of a point because we're tracking the y, which is up and down. Okay, and then for cosine, we're tracking the horizontal displacement of a point as it rotates around the unit circle. And we also know, based on our previous knowledge of cosine, that cosine actually tracks x over r. So it should make sense, because we're dealing with x here, that we're actually tracking the left and the right of that point. So whenever you think sine, I want you to think vertical displacement, and whenever you think cosine, I want you to think x or horizontal displacement. Okay, so let's take a look at how we can use these functions in actual sinusoidal function examples of periodic motion. Now, when we talk about periodic motion, I want you to think about anything that has a rotation over a constant speed or a constant rate. Things like this can be a Ferris wheel that rotates at a constant speed, carousels, merry-go-rounds, even clocks, they rotate around, the hands of a clock rotate around at a constant speed. Anything that's kind of like has this like circular motion. We also talked in a previous worksheet about like a circular luggage carousel. So if you imagine those carousels at the airport, when those start up, the conveyor moves at a constant speed and the luggage continually rotates around until someone picks it up. Okay, so we're going to take a look at an example of a Ferris wheel, and we're going to track the displacement, the vertical displacement of a little cart, one of those ones that you sit in, as it rotates around counterclockwise. And in this case, we're going to start our tracking when the cart is on the positive x-axis here. So that's this point right here. And the radius of this Ferris wheel is 8 meters. So when you draw your circle here, I already have pre-drawn mine, you're going to make sure that it's 8 units in all directions. So you kind of see that mine is crossing at the points 0, 8, or sorry, 8, 0, 0, 8, negative 8, 0, and this point here would be 0, negative 8. Okay, so the important thing is that when you're graphing or doing applications with rotations, your starting position is 0 degrees. So yes, we have our normal 90, 0, 90, 180, 270, 360 locations, but those actually don't tell us the rotations of our actual cart. In some cases they can if the start is at the normal 0 degree location, but you would need to be rotating counterclockwise and you would need to be starting at the normal 0 degree location. So in this case, that's actually the scenario. So we're starting at 0 degrees, and every point that I rotate to here, as I rotate from red to blue to green to pink, and then back to red, I'm rotating 90 degrees each time. So in this case, when I look at my points and I rotate around, I'm actually interested in vertical, which means I'm actually interested in all the y locations as we rotate around. Okay, so I'm going to kind of show you what I mean. So my vertical displacement is going to be my y here, and this is going to be measured in meters, and the rotation of the cart around here is going to be measured in degrees. That's going to be like my x. And if this is my start, we start at 0. If this is our start here, the vertical displacement of the cart of my Ferris wheel is above, below, or equal to the center. What is it? Well, it's actually 0 meters above or below the center, right? It's actually equal to the center here. And I know that as well because my y coordinate here, that's actually what tells me about my vertical displacement. It's actually 0. So at 0, I'm at a vertical displacement of 0. And we also want to just mark off our scale of our y-axis, and I need it to go up to 8 because my radius is 8 here. Okay, so at 0 degrees, I am at a vertical displacement of 0. Now we're rotating counterclockwise as the question tells us, so I'm going to rotate now up to this location right here. So now, how far have I rotated from my initial starting point? Well, I've rotated 90 degrees from my initial starting point. So at my 90-degree rotation, what's my vertical displacement? Am I above the center, below the center, equal with the center? Okay, so I actually see here that I'm above the center, 8 meters. So at 90, I should be 8 meters above the center of the Ferris wheel. Okay, now let's rotate to our next location. That's this location here. And how far have we rotated from our starting position? So what's this rotation all the way around? Well, that's actually 180 degrees. And at this location right here, am I above, below, or equal to the center? I'm actually equal to the center. I'm not above it and I'm not below it. So my displacement should be, vertical displacement I should say, should be 0. So I'm going to graph 180, 0 over here. Okay, and then we'll rotate to the next position, which will be this guy. And I've now rotated 270 degrees from my initial starting position. So at 270 degrees, what is my vertical displacement? Am I below the center? Am I above it? Or am I equal to it? Well, this is the center right here. I can see I'm actually 8 units below the center. I'm actually at -8 meters below the center. So we'll mark a point at 270, -8. And then rotating back to our initial position, now I've rotated a full 360. And I'm back at 0 meters above or below the center. Okay, looking at that y coordinate there. So I have the point 360, 0. Now we're going to just connect our points. Nice smooth curves here, no zigzags. And there's our track of how our cart moves with rotation versus vertical displacement. And if I wanted to make an equation for this, let's say, I would say maybe displacement at some rotation theta is equal to, this is essentially a sine function. Remember we said when we think vertical displacement, we want to think sine, but this sine function has an amplitude of 8 rather than an amplitude of 1. So that simply means that our a value is 8 rather than 1. Okay, you don't have to do this. I just want to help you kind of understand how these are related to what we've done in our previous lessons here. Okay, let's take a look at another example. Now we're going to use the same scenario, except we're going to graph the horizontal displacement versus the angle of rotation at the same starting point. So you're going to just recopy out those points that you did in part A. Okay, so those 4 points are now there. And because this is my starting point, this is going to be 0 degrees. So you can just cross out the other ones, but they are really going to be the same because we're starting at the normal 0 degree and we're rotating counterclockwise. Okay, so we've got that. This is our starting position. And now I want to graph horizontal displacement. So as I rotate around, I'm actually going to be interested in each of these x coordinates here. Okay, so let's write this as horizontal displacement in meters. And the x is going to be the same for this one. This will be the rotation in degrees. And I do want to make sure, so really I'm going to have the same scale here. It's going to go between -8 and +8 because my radius is the same. All right, so at 0 degrees, horizontally, where am I in relation to this center right here? Well, horizontally, I'm actually 8 units to the right of the center. So I'm at a horizontal displacement of 8 units. So I'm going to graph a point at 0 degrees, 8 meters. Okay, now we're going to rotate to the next location, and I've now rotated 90 degrees from my starting position. So now we're actually at 90 degrees from where we started, and are we to the right or the left, or are we equal to the center here? So we can look at the x coordinate here, and that actually is showing us that we're 0 units to the right or left of the center. So our horizontal displacement is 0 at this particular point. So we're going to plot 90, 0. Okay, now let's rotate over to the next important point here, and that is 180 degrees from where we started. And are we to the right, the left, or are we equal with the center now? Well, I can actually see I'm 8 units to the left of the center, and that would be a horizontal displacement of 8 meters left, or in other words, we would go 180, negative 8. So that's what we're going to graph over here. And rotating further here, now we are 270 degrees from where we started. And are we to the right, the left, or are we equal to the center? Well, I think we're actually exactly equal to the center, and the x-coordinate tells me this as well. So we are at 270 with a horizontal displacement of 0. Plot that point. And then our final point, we've now rotated a full 360 from where we started. And now we're back at 8 units to the right of the center. So we're going to be at a horizontal displacement of 8. Now we're just going to connect these on our graph, nice smooth curves. And there is our graph tracking horizontal displacement. Now, because we're tracking horizontal displacement, perhaps a formula that we could come up with for this one would be a cosine equation. This is a regular cosine function. It starts on a maximum, but its amplitude is 8 rather than 1. So we change the a value to 8. Okay, now what happens if I track vertical or horizontal displacement and I don't start at this usual 0 degree location? So we're going to take a look at that in part C here. So I want you to copy out this circle one more time, and we're actually just going to erase these values in here so you guys can just cross that out there, because we're going to track our own rotations. These may change if your usual starting position changes, and you're just going to plot out these points one more time. 8, 0, 0, 8, negative 8, 0, and 0, negative 8. And we're going to suppose that our new trip of our Ferris wheel cart is actually starting at the bottom of the Ferris wheel. So we're starting here, and we're graphing vertical displacement. So I'm interested in all the y's as I rotate around this circle. Okay, so remember guys, your starting position is always where you start at 0 degrees. You're tracking the rotation, and where you start, you've rotated 0 so far. So at 0 degrees, what is my vertical displacement? So before we do that, maybe we can just label this here. This is going to be vertical displacement in meters, and this will be the rotation in degrees. And same scale as last time. Okay, so at our starting position here, what is the vertical displacement? Are we above, below, or equal to the center? So I think we're actually 8 units below the center. So we should be at 0, negative 8 to start. So there's our first point. Now we're still rotating counterclockwise here. So if we rotate, let's say up to this location, we've now rotated 90 degrees from where we started. And what is my vertical displacement? Am I above, below, or equal to the center? So I think I'm actually equal to the center here. We're at a displacement of 0 meters at 90 degrees. So we're going to plot that. Okay, and then next location here, we've now rotated 180 degrees from where we started. And look at the y coordinate at that location. We are at a displacement of 8 meters above the center. So we're going to go and plot that point here. Next location here, we've now rotated another 90 degrees, so that is 270 degrees from where we started. And looking at the y-coordinate here, we can see we are 0 units above or below the center, or 0 meters. And then finally, we're going to rotate right back to where we started here, so that will be a full 360, making a full rotation or one full cycle around the Ferris wheel. And now we're down 8 meters below the center. So let's graph those last 2 points, 270, 0, and 360, -8. And we're going to connect those with a nice smooth curve as usual. And there's our function. So typically we would say, maybe we'll call this displacement at rotation theta. This is a sine function because we know we can also express this as cosine, but typically when we see vertical displacement, we want to think sine function. It has an amplitude of 8, as we mentioned above. And now the shift is actually different. So if you think about your midline here, our midline is actually along the 0 or the x-axis. And where is our rising midline? So if I trace along that midline until it starts rising, my rising midline is actually 90 units to the right. So this is going to be our d of sine. So what I'll do is I'll do theta minus 90 degrees. And this actually makes sense as well when we think about our graph over here. I started 90 degrees before my usual 0 degree location, right? So it makes sense that it's kind of shifted everything by 90 degrees from where it usually is. So that's kind of how we would say our equation for vertical displacement in this scenario. Okay, let's take a look at another scenario here. We have a carousel, and I want you to imagine we're looking at this carousel from a bird's eye view. It has a diameter of 15 meters, and we're going to track the path of a horse directly in line with the center horizontally as it rotates around the carousel 3 full times. We're going to create a graph that models the horizontal displacement of that horse as it rotates around in a clockwise direction. And I'm going to say that our starting position, because it just says directly in line with the center horizontally, I'm going to say it starts on that negative x-axis part. And when we think about diameter, I actually want to consider that the radius of this is going to be 7.5 meters. So you're going to create a circle. I've already done this, but you're going to create a circle that is about 7.5 units in all directions. And we're going to graph our points along here. And I'm just going to eliminate, you can just cross these out because we're going to have new rotations based on our rotation theta and based on our starting position. So plot out your points here. We're going to have the point 7.50, 0, 7.5, negative 7.50, and 0, negative 7.5. And I said that our negative x-axis was going to be our starting position. So this is going to be our 0 degree location. And because we're tracking horizontal displacement, I'm actually going to be interested in all the x coordinates of these points as we rotate around. Okay, so that means maybe we can, this will be our horizontal displacement. Again, this will be in meters. And this will be our rotation in degrees. And we're going to scale our y-axis so that we can fit up to 7.5 in both directions. So I'm thinking we'll go by ones here in both directions. And then we'll be ready. Okay, so remember wherever you start is 0 degrees and we're tracking horizontal displacement. So I'm interested in, are we to the left, the right, or equal with the center? So at this point here, we're actually to the left of the center by negative 7.5 units or 7.5 meters to the left. So we're going to start at 0 degrees at negative 7.5. Okay, now we are also rotating clockwise. in this question. That's an extra little stipulation that I added there. So we're actually going to rotate this way. And now I've rotated 90 degrees from where I initially started, and I'm at a horizontal displacement of 0 meters. I am equal with the center horizontally here. So let's plot that point here, 90, 0. Okay, rotating to our next important point here, we are at 7.5, and we've now rotated 180 degrees from where we started. Okay, so we are right 7.5 units. So we're going to rotate up to 187.5. Okay, next important location is here. We've now rotated 270 degrees from where we started, and we are exactly in line with the center. So we are 0 meters as far as horizontal displacement. And finally, back up to where we started, we are now at a full rotation of 360 degrees, and we're back 7.5 meters to the left, or negative 7.5 on our graph here. So we'll plot that. Now, as I continue to rotate around here, I'm rotating every 90 degrees, and I'm going to return back to the same locations that I did before. So now if I continue to rotate around, I'm now at 450, 0, really just kind of completing this pattern here. And then if I rotate another 90 degrees, I'm now back over at this location. I'm 7.5 meters to the right of the center. Another 90 degrees, I will be back at this location, which is at another 90 degrees will be 0. And then back up to our same location. So a full 720 from where we started. And then we're going to complete the cycle one more time. So 90 degrees later, I'm going to be at a horizontal displacement of 0. 90 degrees after that, I'll be up at 7.5 here. 90 degrees after that, back down at 0. And for a full rotation, we'll be at 1080 at negative 7.5. So this gives us 3 full rotations around that carousel. So we're going to connect all these points now. No zigzags, guys. Create some nice smooth curves here. And there are our 3 cycles. Okay, so there's our graph. If we were to imagine this as a cosine function, we would have displacement at some rotation theta. Our new amplitude is 7.5. And what would our rotation be here? Well, if you think about our rotation, I would be looking for the nearest max. This actually happens 180 to the right. So we would say negative 180 degrees for our rotation. Okay, and the C value is still at 0. That's our midline. And our period is still 360. So K would be 1 and C would be 0 here. So there you have it. Okay, now we can also track, rather than horizontal displacement and vertical displacement from the center, we can also track horizontal and vertical displacement from the ground. So in this last example, we're going to take a look at a Ferris wheel, and we're actually going to track the height of the rider above the ground using a sine function. And so what we're going to do here is we're just going to first create a picture of what's going on with our Ferris wheel. So I want to imagine that we're looking at this from a side view. And here's our Ferris wheel. All right. So here's what we want to track here ideally is I want to say I have a ground here, and I really want to track the height of the person as they are above or below the ground. And then I'm also just going to mark off here where the center of this is, kind of like where these important points are here. So This and this will kind of be my important quadrants here. And I'm just gonna move this guy down just a little bit so he's right in the center. Perfect. Okay, so assume the rider enters a car on a platform that is located around the rim 20 degrees before the cart reaches its lowest position. So let's say they're entering about here. And this right here is 20 degrees. So this is going to be our start. This will be our 0 degree location. And I'm also just going to mark off how far my person would be at these important points around here. So how high is the minimum off the ground? So this tells us that this is 6 meters above the ground. And then at our next location, this will be an important location. How high are we here above the ground? Well, if I'm 6 meters from here to here and I have a diameter of 15, that means that this must be 7.5. Okay, radius of 7.5, which means that this is 13.5 meters off the ground. And then next location here, this will be the maximum height of the rider all the way from the ground up. So if this is 6 meters and the whole diameter is 15 meters, the maximum must be 21 meters. So that will be at this point here, that's the maximum height. And then finally, down here at this location, I'm going to have the same height as before. So the same height as this. So this will be 13.5 meters off the ground. Okay. And 0, how high is this off the ground? This is going to be just above 6 meters, but I can actually calculate this using Pythagorean theorem. So let's just I'm just going to show you. Here's our triangle here. And if I can figure out this height right here, we'll call that h. I should be able to figure out this remaining height over here. So if I zoom in on this triangle a little bit, what I know here is that the radius of this circle is 7.5. That's actually the hypotenuse of the triangle. And do I know this rotation inside here? Well, if this guy is 20, then this must be 70 degrees. So I'm going to enter that into my calculator, or into my triangle rather, and I'm looking for this. So if I know this is 70, that makes this opposite. Maybe I shouldn't have called that h. Maybe well, it's fine. This is opposite, and this is hypotenuse. So I'm going to use sine of 70 equals h over 7.5, and that means that h equals about 7.5 times the sine of 70. Make sure you're in degree mode. So this is about 7.04, we'll say 0.5. So that's this. What I really want to know is this little red thing here. So if I know that this whole thing is 13.5, I should be able to subtract that to get this. So x is equal to 13.5 minus 7.05. So x is approximately equal to about 6.45 units or meters. So that's my starting position there. All right, so we are going to label here. This will be vertical displacement above the ground in meters. And this will be, as usual, a rotation in degrees. And I want to make sure that I can go all the way from 6, which is my minimum height, up to 21. So make sure that your y-axis can go all the way up that high. So let's say if we go by 2s here, I think that should give us enough that we can fit everything that we need to fit. Perfect. And I know that my starting height, so remember we said this was 0 degrees. Now we know that our starting height is actually 6.45. So you're just going to kind of like approximate that. It should be just above 6. And then we are going to rotate, we are rotating counterclockwise here, I think. Yeah, it says 20 degrees before it reaches its lowest point. So I probably should specify here, we are going counterclockwise. Okay, and that means that we're rotating down here to this next most important point, which is the minimum. So how far have I rotated from here to this new point here? Well, I've actually rotated 20 degrees. So now this is going to be 6 meters at a rotation of 20 degrees. So if this is going by 30s, this is 30, 60, 90, and so on. We'll just mark those off here. That means that 20 degrees is probably about like here. So that's going to be our 20, and we're at 6 meters above the ground. Okay, so we already kind of figured that out. The drawing is key here because that's really going to help you visualize where your cart is as it rotates around here. All right, now we're going to rotate up here to our next important location. And how far have we rotated from our starting position to here? Well, I rotated 20 degrees in this little slice here, and then 90 degrees. So I've rotated now 110 degrees. And I'm at a height of 13.5 meters above the ground. So 110 is about right here. And I am now at about 13.5. So I want to graph that right about here. Or maybe a little bit further to the left, maybe like here. There we go. Looks pretty good. Okay. Now rotate to your next important location. I'm now rotating another 90 degrees. So I'm rotating from 110, 90 degrees. So that means that I've now rotated 200 degrees from this initial starting position down here. And I'm now at a height of 21 meters. So 200 degrees, that's going to be about here. And you're going to go all the way up to 21 meters here. That's going to be about here. Okay, keep rotating. Now we're going to rotate another 90 degrees to get to this new location. So that will be 290 degrees from our starting position. And we're at a height of 13.5 above the ground. So 290, that's going to be about here. And we're at 13.5 again. And then rotate back to your original starting position. This is now this is now another 70 degrees. And we're back to our initial spot here. So that's actually a full rotation of 360. And we're back at our starting height of 6.45 meters. So you're going to plot that just above the 6 meter mark here. And that should give us a full rotation. So here's what we've got. Okay, so there we go. There's our height of our rider above the ground if they start 20 meters before the lowest point. And this is actually asking us to model with a sine function. So when we say vertical displacement, maybe we can say height above the ground at a rotation of theta. And just as a little tip here, your radius is always going to be your amplitude of your function. So you can do max minus min over 2 here if you want. That would be 21 minus 6 over 2. But if I know that the diameter of this is 15 meters, then I know the radius is 7.5, and that's actually going to be the amplitude of my function. So that's the amplitude. My period is still 360. It takes me 360 degrees to rotate around, which means k equals 1. And here I have theta. And where is my rising midline? Well, my rising midline, so if my midline is 13.5, that's this right here. I guess I kind of just told you the C value there. But this will always be, whatever this displacement is, that will be your midline. So that's actually your C value. And if I'm looking for a sine function, I'm actually looking for the rising midline. And this right here is the location of the rising midline. This happens at 110 degrees. So that is actually my shift, 110 right. And the midline, max plus min over 2, or you can just kind of look at what you found here, is going to be plus 13.5. So there is a sine function. You can use h at x, you can use v at x, whatever, it doesn't really matter. Or you can even just say y equals, and then you can use the variable x here. That's totally fine. But in applications, sometimes we like to say like height at rotation theta, or like something that actually relates to the application itself. Okay, and then finally, we are going to model the height of the rider above the ground using a cosine function. So as we know from our previous lessons here, when we model using a cosine function, everything is going to remain the same except for the d-value shift. So in order to find the d-value shift, let's just look at where our maximum falls. So our maximum falls to the right of the y-axis, and this is occurring at 200 degrees. So you are going to express this with minus 200 inside your cosine function there.